Okay, as I was saying before I was so rudely interrupted by the camera, talking about the speed and the relationship between the frequency, the wavelength, and the wave speed. If we have a single wave traveling between different media, so let's say you have a beam of light that starts in air and enters water, or starts in glass and enters quartz or diamond. As it changes media, it will change speed. However, if it's a single beam of light, the frequency is constant. So you have to keep this straight in your head. If we have a given medium, a medium that is constant, the speed does not change. However, if we have one beam of light going between different media, the speed can change, but the frequency remains constant. Okay? Frequency is constant. Upon changing media, once it changes media, didn't think that was going to happen. Come on. Upon changing media, the speed and the wavelength. Remember this, where am I? Oh, I know what I did, okay. By the way, the symbol for wavelength, I don't think I mentioned it last time, is this funny looking, I think of it as like a 7 with a leg sticking out to support it. It's called a lambda. So this is a lambda. If you hear me refer to lambda, that's what I'm talking about. Upon changing media, the speed and the wavelength change, but frequency remains the same. You have to keep these two cases straight in your head. Okay? Whether you have a given media or you have one beam of light going between different media. You have to keep those straight. Okay, sorry, that's a lot of writing. Let's erase this. Let's go to some pretty simple examples to start off. You know, kind of the only math that you're really going to see for today. I shouldn't say that. Like I said, I think I'm gonna need one more video after this. Come to a little over an hour with this sort of stuff. Okay, examples. Speed of sound in air is about 340 meters per second. What is the wavelength of a musical note that oscillates at 440 hertz? That means this sound goes through 440 cycles per second. This is a very simple question, very, very straightforward. We know the relationship between the speed of a wave, its frequency, and the wavelength. We are looking for the wavelength. We are given the speed, 340 meters per second. We are given the frequency, 440 hertz. We are solving for lambda for the wavelength. I'm not going to do the calculation myself, but I wrote down earlier that it is 0.77 meters. Makes sense given the numbers that we were given. Question 2. If the frequency of the above sound doubles to 880 hertz, what other changes occur in the wave? So this isn't asking, we're not saying that we're like taking this particular sound wave and doubling it. Let's just double the frequency. Okay? Doesn't say we're changing the medium. Says nothing about doing this in anything except air. So if F doubles, since we're still dealing with the same media, V remains the same. Because we're in the same medium. However, looking at this equation, if the frequency doubles, but V stays the same, in order for the right-hand side to still be equal to the left-hand side, this is constant, this goes up, it doubles, the wavelength has to decrease. And more specifically, the wavelength must get cut in half. It is halved. Okay. And we could actually figure out what this new wavelength would be. Okay. Higher frequency typically means lower wavelength, especially if we're dealing with a similar speed or the same speed. So real quick, V equals F lambda. The speed is still 340 meters per second. The frequency has now increased to 880 hertz. That should result in a wavelength of approximately 0.385 meters. Half of what it was originally. Last question. What if this 880 hertz sound wave entered a new medium, such as a wave in air entering water? Now I'm not going to get specific with numbers here, but we can, again, just kind of explain what should be going on. If we take this particular wave and we send it to a new medium, anytime a single wave transfers between medium, what stays the same? That would be the frequency. So the frequency stays the same. Let's use the example of air and water. Okay, let's use that example. So speed, we know, increases with a denser material. Speed of sound is greater in water than in air. So we can write down the speed. Okay, speed increases, and again, please remember, because I just noticed another error in my notes. I'm just catching lots of errors today. Please remember we're talking about sound waves right now. For a sound wave, denser material is higher speed. It's reversed for a light wave. A light wave, denser material, is lower speed. So V increases. Because denser material. Velocity increases because there is now a denser material in the way, and therefore the wavelength actually also has to increase. So it's kind of, we probably should have swapped the order of these. So the velocity went up, frequency stayed the same. That means the wavelength would have had to have gone up. Okay. If we had maybe an actual speed for the speed of sound in water, which you can look up very easily, then we would be able to actually calculate what the new wavelength would be. Okay. To finish off, we have three phenomena, three things that happen with waves that you need to see. The first one is beats. Bears, beats, Battlestar Galactica. Not those type of beats. Okay? Beats as in musical beats. And not, it's still a little bit different than you would learn about in class, or at least we call them something a little bit different. Let me get something up on the board for you. Okay, let's see. Not that yet. Okay. Hopefully you can hear this. Okay, I'll turn it up a little bit louder. Okay. Hopefully you can hear it. If it is causing you intense pain, I'm very, very sorry about that. But right now what I have, what I was just playing is 2 pulses of sound. This is supposed to be used for headphones. One goes into the left ear 500 hertz, one goes into the right ear 500 hertz. And you can hear that it's a consistent sound. If you're a musician, you would say that these 2 pitches are in pitch. They're tuned up. It's the same exact pitch. Now watch what happens when I change one of them to be 501. You can hear the sound kind of go in and out. You can hear a spot where it's a little quieter, a spot where it's a little louder. That is called a beat. The reason that there is a beat here is because of this slightly different frequency. Okay? I can increase the number of beats per second by widening these even farther. You can hear it pulsing a little bit more now. If I go up to like 506, or no, let's do 503. Starts to get real annoying pretty soon. Now it's really obnoxious, okay? What this is, there, I'll stop torturing. What this is you have two different frequencies, okay? And if those frequencies match up perfectly, you hear just an unbroken pitch. But if they are off by a certain number, then whatever the difference in the frequency is, there will be that many times per second that the pitches are doing what we call canceling each other out, which we're going to talk about a little bit later. Destructive interference is what we talked about last year. That's what this is. So if you have 500 and 501, once per second there will be destructive interference. It will cause the sound to cancel out. Right now I have 500 and 515. That means 15 times per second, very, very rapidly, there will be 15 times per second that these pitches are undergoing destructive interference. That is what a beat frequency is, okay? That is what beats are. So let's write this down. Okay, you can play along. That's kind of a neat little website. Online tone generator, binaural beats is the backslash on there. It's pretty easy to find if you just Google online tone generator. I'm sure you could go down to it. Pretty easy. So let's write this down. So beats. Here's what a beat is. If you have some waves, and these waves have similar but not exactly equal frequencies, then we end up hearing something called a beat frequency. The beats that you heard were the ebbs and the flows. So when it was like you can count, I mean, whatever cycle you want. You can either count the quiet parts or like the loud parts where it seems to be flowing towards you. That's the beat frequency. You count how many times that happens per second. And it turns out that the beat frequency, the number of times you hear that per second, is simply the difference in frequency, the difference between those two frequencies. So, for example, before we get to the example, the way that you hear this, and you guys, if you're in choir or you're in band, you have heard instruments being out of tune, and it's not a pleasant sound. And you've heard instruments being very close to in tune. The reason that something sounds in tune is because the beat frequency is very close to zero. If something is not in tune, then you hear a beat frequency that's a little bit higher, okay? And you would think that if the bigger the beat frequency goes, the worse it sounds. Like, oh, if you have a difference of like 200 or something, it's terrible. That's not really the case. Music is very interesting in pitch. It depends, it's like certain multiples of certain numbers sound really good together. So like playing a certain chord, like I remember like B flat, D, F, and another B flat. You know, you've got your standard chord or whatever. Like those are tones that are a certain amount of hertz frequency apart that sound good together. A big gap in frequency. But a lot of times if you're really close to the same number, but you're not quite on the same number, that is when it sounds really, really bad. Okay, so again, you hear this. You hear beat frequencies when you're talking about musical instruments. And when that happens with musical instruments, we just describe them as, oh, you guys are out of tune with each other. So let me give you an example. So let's say if instrument 1 plays a note at 520 hertz and instrument 2 plays a note at 516 hertz, what do you hear? Well, the difference between those two numbers, 520 and 516, is 4. Okay? The beat frequency is 4 hertz. So what do you hear? You hear 4 pulses. Okay? You hear 4 of those. And again, what that really is destructive interference. Per second. So I think one of the homework questions, maybe not on this multiple choice, maybe it's on the other one, is like a note is played and you know it's 537 hertz and you hear 7 beats per second. What are possible frequencies for the other instrument? Okay. Well, 537, 7 beat frequencies, that means it's 7 away. You've got 2 choices. You pick whichever one it is, either 530 or 544. Obviously different numbers for the homework. Okay, second thing I want to talk about, Doppler effect. You know what the Doppler effect sounds like, even if you can't describe it in words that well. The example I always give is the speeding ambulance. Or actually, I just heard it the other day with a helicopter going overhead. There's a helicopter that went over my house Sunday afternoon, and you could hear the difference in pitch as it transferred from one side of the house to the other. So, anyways, back to my example. With a speeding ambulance, okay, or anything that's moving really fast and emitting some sort of sound. Coming towards you, what does it sound like? Well, probably kind of like normal. But when it's coming toward you, you notice that the frequency is very high. It's like really, really high. And then when it gets past you, the frequency drops. And I mean, little kids know how to do this because they listen to sounds when cars go past. And they'll go, okay, you see how the frequency, the pitch dropped? Up here I was like, and then when it went past, it was, that is the Doppler effect in action. Okay? It's the easiest way I can put it. So, with the speeding ambulance coming towards you, it is making, to your ears, a high-pitched sound. Going away from you, that sound seems like it changes pitch.